The subject of this afternoon's webinar is high-performance replication with DRBD for Dolphin Express. And what we're going to be showing you this afternoon is an exciting combination of two technologies aimed at providing extremely low latency storage replication for high availability solutions. As I said, my name is Florian Haas. I'm with Limbit here in Austria. Joining me is Joachim Borringen for this afternoon. He's a software architect at Dolphin Interconnect Solutions. And what you can expect from this webinar is outlined in this brief agenda that we're having here. First of all, we're going to give those of you who are already familiar with DRBD, but perhaps not as familiar with Dolphin Express, a quick rundown of the basics of Dolphin Express as a technology, both the hardware technology itself and SuperSockets, the software stack associated with it. Then, for those of you who have previously been familiar with Dolphin Express, but perhaps not so much with DRBD, I'm going to give you a quick rundown of the basics of DRBD, what the technology is, how it works, and what its key benefits are. We're then going to be talking about how to actually set up and configure a DRBD for Dolphin Express replication setup. You will find out that it's actually quite easy and can be a very, very smooth replacement for the Ethernet and TCP-based replication that the majority of you are going to be using at this time for DRBD. We're then going to take a look at performance considerations, particularly the very, very positive impact that DRBD and Dolphin Express combination has on reducing latency for highly available replicated storage solutions. And of course, we're going to go over some of the applications that will benefit greatly from this new combination. So for the first part of the webinar, I'm going to yield the floor to Joachim, who's going to give you a brief overview of the basics of Dolphin Express, the hardware and the software stack associated with it. Joachim, please.
Thanks, Florian. Welcome, everybody, from me. Joachim Borringen. I work for Dolphin Interconnect Solutions. For those of you who may not have heard of us, we are in business since 1992. Founded in Oslo and still with headquarters in Oslo. And we have, since 1992, produced chips and hardware using these chips based on an interconnect standard named iSCSI. These chips are used in large shared memory servers from Data General and other companies to create a large shared memory, but they're also used in embedded solutions for aircraft, medical products, and other demanding applications concerning the applicability and the performance to provide an interconnect, high-performance interconnect, which is not memory-based in this case. So when last year we merged with Stargen, which is a company also in the interconnect business, located near Boston. So we now have a branch in Boston, USA. And with Stargen, we have acquired the new interconnect technology generation, which is what we're talking about today, named DX. And the DX interconnect is, if you can see it on the next slide, it's first just a simple piece of hardware, as you know it, like a NIC, and it's a PCI Express board with an X8 interface. You can also use it in an X4 slot if you don't have X8. The performance penalty is not so big on latency, and it's a small little profile card. It fits in really every server that has a PCI Express slot. It has low power consumption, which means you don't have to worry about additional cooling requirements for your server. And it has some features that set it apart from other network interfaces or interconnects, and which provides performance that we will see later on. So it has features like transparent remote memory access. So a CPU can just access memory located on another machine as if it was local. It has also very efficient DMA engines for bulk transfers, and it provides means to have a very fine-grained interrupt control to avoid sending and processing interrupts when not needed, which is a major problem for for heavy load scenarios if you create too many interrupts. So for a DRBD setup, you will use typically 2 of these adapters, 1 in each machine, and each adapter has 2 ports with 10 gigabit each, and you can use both of these ports together, and they are bonded on the hardware level, so transparently and redundant, and they effectively provide twice the bandwidth, so 20 gigabit effectively. Unlike what you may have experienced with Ethernet, where bonding does not work so well. Here we have perfect scalability as it is done on the hardware level. We also offer switches for this interconnect, but for standard DRBD setup you won't need a switch. It may be interesting if you decide to use Dolphin Express not only for DRBD but also for other applications in your cluster where you need more than 2 nodes. Good. We can see that Dolphin Express is not only a piece of hardware, but it's also a very sophisticated software stack. And what you will see from this software stack is the component named SuperSockets. SuperSockets are basically just full BSD sockets as you know them, as nearly everyone uses them in the applications. So DRBD uses BSD socket in the kernel. iSCSI, for example, uses these sockets for communication in the user space, and SuperSockets replace standard Ethernet sockets with our own very high performance implementation of these sockets. They bypass most of the software layers, as we will see later on, and therefore provide very low latency and also, of course, high bandwidth. SuperSockets are not brand new. They are on Linux in use for production use for more than 3 years now. And the main application is databases in general, MySQL cluster specifically, and also customers have implemented their own synchronous application mechanisms with SuperSockets. They are, of course, because it's our own software stack, they are very highly optimized to our hardware, so we can achieve less than 2 microseconds process-to-process latency between machines, and currently about 1.3 gigabyte bandwidth peak. And next to the optimization for the hardware, we also combine with our partners like Limbit for DRBD to qualify and fine-tune SuperSockets for the specific application. And another important aspect is that we made a lot of effort to make it simple to deploy in new and also in existing setups, because it can be used as a performance booster, where when you notice that Ethernet doesn't deliver you enough performance for your requirements, you can just plug in our hardware and install the software and don't need to change anything in your configuration, because SuperSockets will just take over your existing sockets and make them fly. SuperSockets are open source, GPL, and they can be used with any 2.6 kernel. So it's not that we are providing binaries for just this and this and this kernel, and if you have another kernel, you're doomed to upgrade or downgrade. You can use our software with any 2.6 kernel.
Okay, and now that Joachim has run you through the Dolphin Express basics, for those of you, as I said, who have previously been familiar with Dolphin Express, but perhaps not so much for DRBD, I'm going to step in and give you a quick overview of what DRBD is actually all about. and how it benefits from Dolphin Express as an interconnect. So DRBD as such is a distributed replicated block device. What does that mean? It is a block device that is to say it sits at the abstraction layer for block-based I/O in the Linux kernel. What that also means is that it sits below any file system layer, below any application layer, and that in turn means that it literally can be used for any application whatsoever as long as it uses a block device, and those that don't are indeed few and far between. So it's a very, very low level of replication technology. As such, it provides high performance. It's very lean and is pretty much application and file system agnostic. So it can literally be used in order to add application redundancy and high availability to just about any application. The replicated part means that all write I/O that's written to the device is synchronously replicated to the second node. This is the core of what provides the storage high availability in DRBD, and what that means in detail is what I'm going to get to in just a few seconds. And distributed means that it always spans 2 cluster nodes. So what do we mean by a replicated block device or a synchronously replicated block device? To illustrate that, I've given you a brief schematic overview here in this slide. So suppose we have a block device that spans 2 nodes, or more precisely, we have 2 instances of that block device on 2 nodes, one of which is the one where the application is currently running. This is the one that we call the primary node, and the other one is the one where we currently don't have an application running, but which still receives all block device updates. Suppose that all of the intermediate rectangles here that I have in this schematic overview represents one block. Now, clearly, a real-world block device will have a lot more than just 14 blocks, but this just serves to illustrate the concept. Now, what do we mean by synchronous block-level replication? Suppose we have an application which, as I said, runs on the primary node, which modifies a particular block on that block device on that node. Then what happens is we replicate this write over to the secondary node, where it is also written locally, then acknowledged back across the network. And then and only then is that write operation considered completed from the application's point of view. So it's either every write is written either on both nodes or from the application standpoint on none at all. This, of course, happens repeatedly and ad infinitum while the application is running. And this is a key performance advantage over comparable SAN or NAS-based clustered solutions. Any cluster solution that operates on some sort of shared storage is, with DRBD, you never have to go through any sort of network stack to read from the device. We can always read locally. So we can always read from local disk and a local bus, which usually has a lot lower read latency than, for example, reading from a fiber channel or from a storage device that we're connected to via fiber channel or iSCSI or any other sort of network-based interconnect. So this is how DRBD operates when both nodes are in operation. When one of these nodes goes away, so suppose, for example, the secondary node, which at this point is our backup node, goes away, then, of course, DRBD does not wait for that node to return in order to complete its synchronous replication cycles. Instead, it will simply allow the application to write locally on the primary node and will keep those modified blocks marked as modified. It can still read locally, of course, and then when that node that was previously offline, say due to hardware failure or scheduled maintenance or a kernel upgrade or whatever, returns, then DRBD simply does what we call background resynchronization. So that means that those 2 block devices are being brought in sync again, and this happens in a fairly efficient manner. It does not happen in a chronological fashion as the blocks were originally written, but it happens as the blocks are laid out on the disk, which minimizes disk seeks and speeds up the resynchronization process considerably. And then when that is done, we basically have a fully redundant system again. Of course, the whole time we can read locally with the aforementioned advantages. Now, of course, clearly, DRBD is a high availability solution, and high availability is something that you build or that you create not to protect yourself against the failure of your backup node, your secondary node, but instead, of course, high availability is what you build in order to protect yourself against failure of the primary node, the one where your application is currently running. So suppose we are in exactly that situation. We have an application that currently runs on this primary node, writes to the device, reads from it. The writes are being replicated and acknowledged the whole time. And now some sort of failure occurs on that primary node, and we simply lose it. This can be due to hardware failure or any other sort of disk failure or whatever, any other sort of failure. And now what happens is a cluster manager comes in. Now this can be Linux HA, aka Heartbeat, which is the type of combination that you most often find deployed in real-world scenarios, but DRBD in and of itself is cluster manager agnostic. This can just as easily be the Replic Cluster Suite or Stila Lifekeeper or whatever. It is now the job of that cluster manager to detect that node failure and then move the application over to the other node. To that end, it does something that we refer to as promotion. That is to say, it promotes the DRBD device on that previously secondary node to the primary status, and now it can restart the application over on the overtaking node. And because, as I said earlier, DRBD replication is fully synchronous, and all the writes that are written to one node are also synchronously replicated on the other, the application now has the guarantee that its view of that block device is exactly the same as it was immediately before the crash of the original primary node, so it can continue right where it left off. That's the basic and primary principle behind DRBD. That's how you build fully shared nothing, fully open source storage, high availability. And here's where Dolphin Express comes in. Now, historically, or traditionally, we only had one replication and synchronization transport that was supported in DRBD, and those were, in essence, TCP sockets based on IP, which would most commonly run over Ethernet. And then we would have basically the BSD socket layer on the very top of that. Now, clearly that is not the most efficient of stacks, specifically in terms of latency. It is ubiquitous, and you can run it on any system out there. But as I said, it's not really, it doesn't really provide killer latency. Why is that? Because we simply have to go through a number of encapsulation steps. We basically have to slap a TCP header onto our data, and then an IP header, and then chop that into Ethernet frames. Encode it using an Ethernet card driver, put it on the wire, and then basically go through the exact same process in reverse order on the receiving end. Plus, we're using a link layer protocol, namely Ethernet, which also is, by today's standards, not exactly minimum latency. Now, the nice thing is that what we can do, and this is what we've introduced in DRBD 827, is we can replace this entire Ethernet IP TCP socket stack with just the SuperSocket implementation from Dolphin, which very, very efficiently uses the Dolphin Express hardware stack to transfer or replicate data over to the peer node, not having to go through all of these encapsulation steps that I previously mentioned, and basically ship those replication payloads very, very directly and in a very straightforward manner over to the peer machine. And this is, as I said, what we just introduced in DRBD 827. Now, for the Dolphin Express and the DRBD combination setup, back to you.
Okay, thanks, Ryan. Concerning the installation or the deployment of our solution, it's pretty simple. You just install the hardware as you install any other PCI Express adapter and connect the cables. And then what is often a delicate thing to do, especially when it comes to Linux kernel modules, is the installation of the SuperSocket software stack. which consists of the hardware driver, the SuperSockets module, and some Eurospace libraries and tools. And because we wanted to support every kernel of the 2.6 line, 2.4 is also had limited support for 2.4. We provide our software as a source archive, but this archive is a smart one. It's a so-called self-installing archive. So you just need to install or need to execute this archive as a self-installer on one of your nodes, of your two nodes in this case, and answer a few questions, simple questions. And then this installer will compile our source on the fly and thereby matching it exactly to the kernel that you are using. And this makes it very easy to deploy it on any setup that you may have configured and would like to continue to use. Probably are aware of the endless chain of updates that some small component update may imply. Once the software, the installer is running and has installed the modules, it will also apply configuration. So by default, it will just replace the existing IP interfaces, the sockets that are operating on these interfaces with our SuperSockets. But you can always specify that only a certain IP interface should be accelerated if you're using multiple interfaces. So you are very flexible in how to configure the SuperSockets. An important aspect of SuperSockets is also that they can actually talk both, namely Ethernet and Dolphin Express. So if an application opens a socket with SuperSockets, it can connect or can accept connections on this socket not only from other hosts that run also Dolphin Express, but it can also accept and connect to other ports that are only using Ethernet. This also simplifies deployment and configuration very much because you don't have to take care which IP subnet can communicate with which other maybe external machine with SuperSockets or not. You can just replace the socket. An interesting aspect is also the deployment. If you are already running DRBD, you may not want to shut down the service because this is why you're running DRBD. So you can actually deploy Dolphin Express to SuperSockets on such a system without interrupting the service by first shutting down the secondary machine, installing the hardware and software stack there, update the DRBD in this if you have not yet, if you are not yet running a version that works with SuperSockets. And when you restart the secondary, you wait, of course, for the resync to complete. And this operation will once run over Ethernet for now because the primary node has not yet SuperSockets available. So this is what we call failover mode. And then you do the same. You fail over the primary to the secondary machine and repeat the same installation steps on the primary machine. Put it up again, and now the resync between the primary and the secondary machine will run over SuperSockets, as will all other operations from now on between your DRBDs. As I just mentioned, the failover mode, I would just like to add that this failover mode will also apply during operation. If you are running SuperSockets and for whatever reason SuperSockets or Dolphin Express hardware fails, for example, it pulls the cable or the adapter should fail for whatever mode reason, SuperSockets can fail over on the fly with your existing connections to Ethernet and continue to run. And once the problem is fixed, it falls forward again to SuperSockets. So this is, of course, a very important feature for high availability. environments.
Okay, before I actually go to before I actually get to the part where we demonstrate this stuff for you, I want to share a few more insights on the performance considerations associated with DRBD over Dolphin Express. Some of these things that I'm going to mention in the next few slides is something that have already been covered to a certain extent in the performance tuning webinar that we did a few weeks ago. However, I want to focus on one aspect more specifically than I did then. So basically, when we talk about I/O performance, or specifically write I/O performance on a Linux block device, there's two very distinct things indeed that we need to consider. One is throughput, and the other is latency. Now, throughput is basically writing as much data as possible to the device in a given amount of time. And throughput is something that is typically measured in megabytes per second or similar. And there are quite a few parameters that may affect DRBD write throughput, such as the rotation speed of your disks, the number of stripes in a strike rate configuration. So in a rate 1+0 configuration, for example, the write throughput generally scales fairly linearly with the number of stripes. Using a battery-backed controller write cache in write-back mode. As always, we want to warn you against ever using a controller write cache if it's not battery-backed, because in essence you're signing in for losing data. But if you have a good battery-backed controller write cache, which will automatically switch to write through mode when its battery gets depleted, and it's certainly a good thing to do in order to boost your DRBD write throughput. One other, and those are factors that affect the disk subsystem, or I/O subsystem more specifically, and the other one is the replication network. So replication network bandwidth is clearly one other factor that affects DRBD write throughput. One thing that we have to add here is that the conventional way of NIC bonding in Linux with the balanced round-robin bonding mode is something that really doesn't scale well beyond two physical links. Indeed, NIC bonding with balanced RR has pretty much detrimental results in terms of replication performance with three or more physical links. So what you can do is you can switch your replication network to a high throughput interconnect, such as, for example, 10 gigabit Ethernet or Dolphin Express. When we compare disk subsystem throughput, network throughput, and resulting DRBD throughput, what we have to understand is, of course, that DRBD can never be faster than either the local disk subsystem on its nodes or the replication network, whichever has lower bandwidth. So, for example, if you consider the three columns on the very left of this graph, is where you would have a comparatively slow disk subsystem capable of pulling something like 80 megabytes per second, and you have a gigabit Ethernet replication network, which is capable of pulling about 110 megabytes per second. So you're resulting, in this case, your disk subsystem would be the bottleneck, and your resulting DRBD throughput or expected throughput would be about 5% or so below the local disk throughput, which would result in something like 72 to 75 megabytes per second. By contrast, if you have a look at the middle group of columns, where we have a fast store or a comparatively fast storage subsystem capable of pulling 150 megabytes per second, but you're using a gigabit Ethernet transport, which tops out at about 110. Then in this case, of course, a replication network would be our bottleneck, and the resulting DRBD throughput that you would expect for streaming writes would be something like about 105 megabytes per second. And then on the very right-hand side, the third group of columns, where we have a fast disk subsystem and a high throughput replication network, such as, for example, 10 gigabit Ethernet, where our disk, for example, would be capable of pulling about 300 megabytes per second. That's also a typical replication bandwidth that you would get on 10 gigabit Ethernet with today's CPUs and RAM. Then we would expect DRBD to top out only about 280, 290 megabytes per second, as we're going to see in a demonstration in just a few seconds. So that's one aspect of I/O subsystem or DRBD performance is throughput. And the other aspect, of course, is latency. And latency refers to a wholly different concept. It's not write as much data as fast as you possibly can, but write the tiniest chunk of data that you can ever write as fast as you can. So give me your smallest write operation and tell me how fast it is. And write latency is, of course, measured in something like milliseconds or microseconds, typically. And here's where DRBD for Dolphin Express, or where Dolphin Express comes in as highly beneficial for DRBD replication or high availability setups. There's, of course, a few factors intrinsic to DRBD that affect DRBD write latency. Some of those also apply to the disk I/O subsystem. Some are DRBD configuration options. But a very, very important option here is the replication network latency. And let's consider for a few seconds what happens in terms of what happens in a particular time frame when an application issues write I/O on a DRBD device. What happens when first we get the incoming I/O? So two things are triggered pretty much simultaneously. One is the local disk write, which if we're actually writing to a physical disk, will take something like 3 milliseconds, perhaps 2 to 3 milliseconds. And then we have a network replication packet that we send on the wire pretty much simultaneously, which will make it over to the peer node in, well, something like about 200 microseconds. Then that disk write gets repeated on the peer node, obviously, and then we get the network acknowledgement packet back. And what we see on the left side now is our latency penalty that actually arises from using DRBD versus just using local storage. Now, when we're actually writing to local disk and compared to something like gigabit Ethernet, we get to a latency penalty of, in well-tuned DRBD systems, which can be anywhere between 7 to 20% additional latency as compared to just writing to a local disk, which is already pretty darn good considering that it buys you full redundancy. But when we compare this to writing to battery-backed write cache, it's a slightly different story, because now when you consider we get the incoming write I/O, now the disk write, so-called disk write, in fact we're writing to battery-backed write cache, which is just as good, takes a lot less, and will now take on the order of something like 100 to 200 microseconds perhaps, and now the network replication packet will take only slightly less time than the local disk write. Then we repeat that disk write on the other end, and now we send the network acknowledgement back again, and now our latency penalty, even though our total latency of the write in absolute numbers is a lot less, our latency penalty percentage-wise looks larger. And that is something where we wanted to improve. And here's where Dolphin Express comes in, because now we get a very, very low latency network interconnect, which means that our network replication is now a lot faster than it used to be. So the disk write to battery-backed write cache hasn't gotten any faster or slower because of that, but our network replication is now a lot faster, and a lot less time passes before we actually get the packet over to the peer node. And now when we write on the peer end, on the secondary end, and then acknowledge back, now our latency penalty has actually declined considerably. In terms of comparison, consider this overview. This scale is basically latency in microseconds. When we just write to raw battery-backed write cache on one of our chip systems here, we achieve a latency of something like about 70 to 80, maximum of 100 microseconds. If we compare that to DRBD over regular gigabit Ethernet, the replication latency is usually on the order of about 250 microseconds. And going to 10 gigabit Ethernet only makes this very, very slightly faster. However, by contrast, layering DRBD over Dolphin Express cuts our latency almost in half. And this is something that we're quite excited about already. However, this is something that's a fairly new addition to DRBD. In fact, we just released it today with DRBD 827. And it's also a new application for Dolphin, so we do expect quite a significant latency drop on top of that in the next few months. And by the way, just for comparison's sake, here is the same graph basically drawn to scale of the latency of just a raw disk without battery back write cache, which is about something like 3 milliseconds or 3,000 microseconds. So clearly, using a battery back write cache is certainly a good idea if you want to reduce latency. And then using DRBD on battery back write cache with Dolphin Express is an even better idea. So before I get to the applications and deployment scenarios for this technology, let me briefly run you through a little demo of this technology. So I hope everyone can see my console now. The first thing that I want to show you is how easy it actually is to get DRBD configured to use Dolphin Express sockets once you have your Dolphin setup actually configured. To that end, have a quick look with me at our DRBD.conf on the system. And I have two resources configured here. One, which as you can see from the resource name, uses a 10 gigabit Ethernet link, and one which uses a Dolphin Express link. And it's actually very, very simple to instruct DRBD to use super sockets instead of regular TCP connections over Ethernet or whatever link layer protocol that you have available. As you can see here in this address line, the only thing that you do is you prefix SCI to the address that you're used to that looks just like an IPv4 address. And this is what instructs DRBD to use SuperSockets transport instead of regular TCP over Ethernet with all the goodies and benefits that come with SuperSockets, including sub-second failover to Ethernet and so forth. As you can see, the nice thing about SuperSockets here is that they use an exactly equivalent addressing scheme, looks just like an IP address in a TCP port. So you just prefix SCI here, and off you go. There is another performance optimization option here that was also introduced in DRBD 827. That's no TCP port. But other than that, as you can see, it's very, very similar to just a regular Ethernet or 10 gigabit Ethernet-based resource. So this is, by the way, this is DRBD 827, pretty much hot off the presses. Just released. The release announcement is going out in just a few hours, but it's already available, and it's what I can use to show you here. So let me quickly unmount all of our DRBD resources here. Oops, sorry. There we go. So DRBD 0 here is the one that uses 10 gigabit Ethernet. And DRBD 1 is the one that uses Dolphin Express. So the first thing that I'm going to do is, just for comparison's sake, I'm going to give you a few micro benchmarks, or a couple of micro benchmarks here on our dev DRBD 0 device, which uses 10 gigabit Ethernet, which I have mounted to /MNT now. So let me do our good old performance benchmark here on /MNT test bin. So this is just a very simple throughput micro benchmark here for DRBD running on 10 gigabit Ethernet. So as you can see, we have a pretty nifty storage subsystem here, which is capable of pulling just about 300 megabytes per second throughput. And this is something that we can pretty much max here with 10 gigabit Ethernet. And now by comparison, I'm now going to mount my DRBD1. As you can see, we have DRBD1, which is our DX Interconnect-based device on /MNT. So I'm running basically the same throughput benchmark here again. And as you can see, we have pretty much equivalent results here, sometimes slightly better results than gigabit Ethernet here. Here even going up to 375 megabytes per second throughput on Dolphin Express. Clearly, this is not the end of the line for either 10 gigabit Ethernet or Dolphin Express. We expect to be capable of much higher throughput here just on the replication network. It's just such that the storage subsystems, the disk subsystems, are not really capable of pulling that much more throughput at this time, at least not the ones that we can lay our hands on. And now on to the latency micro-benchmark, and this is where Dolphin Express comes in as much more of a benefit indeed than on gigabit Ethernet. So let's quickly take a look at our 10 gig Ethernet mount again. So this is here WP0 again mounted on /MNT. So hang on a second. So now what I'm doing is, instead of writing a large chunk of data and then measuring its throughput, and remember earlier on I wrote an entire gigabytes worth of data in one large chunk. Now what I'm doing is I'm going to write 1,000 tiny little chunks, tiny in this case meaning 512 bytes, which is the hard sector size on Linux. You can't write onto a block device in increments smaller than 512 bytes. So that's exactly what I'm doing. I'm doing 1,000 synchronous sector writes, and I'm going to take a look at how long this takes us on gigabit Ethernet. And as you can see, I'm taking about 0.25 seconds for 1,000 writes, or in other words, about 250 microseconds per write here on gigabit Ethernet, which is exactly what I said earlier on, which would be your typical latency in gigabit Ethernet. And now, by comparison, the same thing on DX. And as you can see, a little slower at first, but we should see very quickly that this is actually dropping down to something like as you can see here, going down to about 100 microseconds here. And of course, it does take some tuning to get this down consistently. There we go. And here, as you can see, all the way down to about 110 microseconds.
If you take more than 1,000 blocks, 10,000, then the results are more stable.
So here we go. So now we're down at about 100, 120, 130, sometimes all the way down to 106 microseconds. So clearly a really good latency improvement here as compared to 10 gigabit Ethernet. And remember, this is just the very, very initial release. This is the first release that has DX support right built in. And we're expecting even better latency drops here as Dolphin DX drivers improve and as DRBD improves over the coming releases. But already pretty exciting technology for us here, and very, very good latency drops that we're already seeing. So let me go back here and talk a little more about applications that will greatly benefit here from these latency drops that we're already seeing. So one typical application would, of course, be MySQL. SuperSocket's already being a fixture pretty much in the MySQL universe as a preferred interconnect for MySQL cluster. Now we can bring DX and DRBD to the non-MySQL cluster world. So, for example, in the typical setup where you have a highly available DRBD-based MySQL master with a number of MySQL slaves, basically getting updates from that with MySQL replication. So then the application can run reports off of those slaves. Now you can use Dolphin Express here as your interconnect for DRBD on your highly available master, and of course you can also use DX as basically a transport layer for MySQL replication. The same type of application, of course, is easily conceivable, or the same type of setup is easily conceivable for Oracle-based database applications with Oracle Data Guard, for example, and a DRBD-based highly available master. Something that will also benefit greatly from this technology is DRBD-based storage clusters. For example, iSCSI clusters based on DRBD as they're marketed by Limbit under the DRBD Storage Enterprise Cluster product name. So this can, for example, be used for virtualization farms or any other type of server farms that has the requirement for using centralized but highly available and replicated storage. So this would be a very, very beneficial deployment scenario. And then, of course, what we market as, we at Limbit market as a DRBD virtualization enterprise cluster, where basically you have a two-node virtualization setup using either the Zen or KVM virtualization technologies, which use DRBD as its storage, its highly available replicated storage basis, now with the considerable latency drops by utilizing the Dolphin Express hardware and super sockets socket layer. Okay, for the summary, I'll yield the floor to Joachim.
Okay, thanks, Ryan. Yeah, a quick summary of what we've seen on this presentation. So supersockets are a mature and compatible add-on to every Linux machine with 2.6 kernel, and provides record low latency, and of course also vast bandwidth, and will in the coming months be fine-tuned for DRBD. And it's simple and convenient to deploy. You even are not required to shut down your service. It's extremely reliable. It is not only, as I mentioned, the capability of failing over online with access to running connections between Dolphin Express and the original Ethernet. We also have watchdogs in the hardware driver, so that if anything goes wrong on the interconnect, the failover will take place, or one of the two channels will be deactivated in a transparent manner. And we support not only copper connections, which are limited to 10 meter in length, but we also support fiber connections up to 100 meter for setups where you have your machines separated by a physical firewall or located in different rooms. So this is really a solution that makes a perfect add-on to DRBD. And concerning the cost, you will, for typical setup, need two adapters called DXH510 and two cables. You can also run with one cable, but two cables are, of course, recommended for maximum performance and redundancy. And everything together, cables and adapter, is currently at a price tag of $1,315. So if you're interested in this, you can directly contact our sales, or that will be my own email address later on. And yeah, as we said, we've been in business for quite a long time, and as such have collected a large number of customers, and can happily add your own name to this list.
Okay. With that, we're basically going to wrap up the non-interactive part of the webinar. As you can see, you can contact either myself or Joachim at one of the email addresses provided here in this final slide. I encourage you, of course, to also take a look at Lindit's website, at Dolphin Interconnect Solutions website, and of course at the DRBD community website. We've almost exactly hit our goal of 60 minutes. What we're going to do now is Joachim and myself, and also Lars Elmberg, of course, core DRBD developer, who's joining us as a panelist. We're going to stick around for another about 15 to 20 minutes to take your questions. Of course, you can type your questions into the Q&A window right now, and you could have done so all along. Please do. You're encouraged to do so. Do watch our website, that's Lindit's website, and of course also Dolphin's website for upcoming announcements and webinars regarding DRBD and Dolphin Express. With that, thank you very much for your attention this afternoon, and a recording of this webinar will shortly be available on Lindit's website. With that, we conclude for right now. As I said, Lars, Joachim, and myself are going to hang around for another 15 to 20 minutes to take questions. Thank you very, very much.
Thank you from me as well.